Hi guys, welcome back. So in this video and in the next few videos, I want to talk about some performance metrics that are widely used in data science applications. So before I start, let's first understand what performance metrics are, right? So performance metrics are basically ways or techniques in which you can quantify how well your model is doing on a real world data set. So there are a lot of performance metrics, and the most common one of them all is the performance metric called accuracy. So how is accuracy defined? It's very simple. Accuracy is just the number of points correctly classified, right, upon the total number of points. Total number of points. Okay, that is accuracy for you. So let's say that you have 50 data points, x1, x2, all the way to x50, and the actual class label for them is let's say 110, and the predicted class labels are 101, and out of 50 class labels, 48 were classified correctly. So your accuracy would be 48 upon 50. This is your accuracy, and that's how you measure accuracy. Now, of course, accuracy is a very simple performance metric to use. It's also very widely used in classification problems, but it's very simple and it comes with its own fair share of problems. So, in this video and the next couple of videos, I want to also stress upon what what performance metric to use in what scenario, right? Because in all scenarios, all the performance metrics don't work very well. So if you look at the formula for accuracy, it's easy to see that if you have a very highly imbalanced data set, like let's say an imbalanced data set where you have 5% positive points and you have 95% negative points. Okay, this is your data set. And a data set like this is very common in real world, especially in medical applications where the positive class labels are the one where the disease was detected, and the negative class labels was the one where the disease was not detected. Okay, so a highly skewed or a highly imbalanced data set like this is very common in medical applications. Now, even now, the problem here is that if you take something like accuracy, the thing is, if you have a very dumb model, let's say dumb model, that classifies all the points that you have as negative all the time, okay, it always classifies all the points as negative. In a case like that, you would still have an accuracy of 95%, which is very high if you look at it in absolute terms, right? So this is one problem with accuracy. It doesn't perform very well on imbalanced data sets, and if you have a very highly imbalanced data set, you should avoid using the performance metric accuracy. Another problem with accuracy is, let's say I have four data points, x1, x2, x3, x4, okay? Let's just say I have four data points and their class labels are 1100, okay? And my predictor or my model that predicts gives me the probability value of what is the probability that the data point belongs to a particular class. Let's say if the model gives me a probability value of greater than zero point 0.5, then the point belongs to class 1, and if it gives me a probability value of less than zero point 0.5, then the point belongs to class 0. Okay, so let's assume that I have two models, model 1 and model 2, and they both give me probability values as outputs for my data points. So the first model gives me something like zero point 0.9, 0.8, and zero point 0.2, zero point 0.1. Okay, my threshold here is zero point 0.5. So greater than zero point 0.5 is 1 and less than zero point 0.5 is 0. And the second model gives me something like zero point 0.6, 0.55, 0.41, and 0.48. Okay. So so if you see over here, the points were classified correctly by both the models. If I take M1 classification, it's 1100. and M2 classification is also 1100, right? So both the models give classified the points correctly. And if I use something like accuracy, I will get the accuracy same for both the models. But it's if you look at the probability values over here, it's very easy to see that model 1 performs a lot better than model 2, right? Because model 1 gives you high probability values for whatever data point it wants to classify in whatever class. And it's performing a lot better than module 2, right? Sorry, model 2, not module, model 2. So this is another problem with accuracy. Although the accuracy in both the models is similar, it's correct. But when it comes to classifying what model performs better, is model 1 better than model 2 or is model 2 better than model 1? Accuracy will not tell us what is which model is better, and it does not consider the probability values. So we'll see how to overcome this problem in the next video.